Okay, folks, let's begin. Everyone can hear me okay? Let me know if there's any problem. Just, speak up if you have a question. So today there's going to be a new topic that we want to begin, which is time-dependent perturbation theory. And then perturbation theory. And this is a really important topic. I think it's one of the most important topics of this semester. It's like, I'd say, regular perturbation theory is a big topic, and then time-dependent perturbation theory is the next really big topic. So this is a really important topic to understand in quantum mechanics. And the point is that in quantum mechanics, we've been up to now, what we've done is we've taken things like, say, particle in a box, my favorite thing. You have these levels in the box, and we talk about particles in the box, and we say, what are the eigenstates? Level 1, level 2, level 3, etc. It could be a box, an atom, whatever. And we talk about all the interactions, spin orbit, relativistic, hyperfine, whatever, or the Coulomb force. We talk about the interactions, and then we say, and what are the energy levels and what are the eigenstates? And that has been our main focus up to now. and so really what we've been focusing on are the stationary states, the eigenstates. And that's important. And that's why we focused on it, because it is a big deal, because it tells us the energies, the allowed energies of the system, which are the eigenenergies. And that's what we measure when we do experiments. So, it's a big deal. But then there's another part of life, which is that stuff happens, stuff happens. We all know things happen. And so that means that your Hamiltonian, when you say that stuff happens, that's another way of saying that your Hamiltonian actually has time dependence. We do not live in a stationary world. The Hamiltonian is not just this frozen thing. We're not all just frozen in time. Things are changing all the time. The Hamiltonian that describes our, what our environment is changing with time. And so then the question is, of course, what happens? What does quantum mechanics have to say about this? In other words, how does stuff change with time? And of course, quantum mechanics has a lot to say about it, because quantum mechanics is really the most basic theory, of how things work, in the universe. And so, so clearly, quantum mechanics is at the heart of everything that's changing with time. Every movement, every change in time. And so, what we want to do is we want to understand that, how does things change in time? And so, that, what we've been thinking about so far is we've been solving this problem, H psi equals E psi. And we've been kind of ignoring the time dependence because it hasn't been so important up to now. But now, if H, the Hamiltonian, goes to H of t, then instead of solving this equation, we have to solve this equation, the original time-dependent Schrodinger equation. I'll write with Bras and Ketz. IH bar ddt psi of t. And you guys have seen this before. You saw it, last semester, and you've thought about this, and you've thought about how this can lead to certain time dependence. And so the time dependence that you guys have thought about up to now has been where you can then say, using separation of variables, this is what you did last semester. You were able to say that psi of xt is equal to some sum, and you had some constants, And then you had all the eigenstates, psi n of x, e to the negative I e n t over h bar, where c of n is equal to. So I'm just reminding you of a formula that you guys did last semester. And this is my wave function at t equals 0. So this is what you did last semester. And this was the formula that you derived and that you used last semester. You said, well, you said I can write my wave function as a function of time as my eigenstates times these phase factors, and I have some coefficient, and I can figure out that coefficient, because if I know my wave function at time t equals 0, I just overlap it on the nth state, on the nth eigenstate, where these are the eigenstates, right? You guys did that. But the point is, though, and this is just a constant. That was last semester. So this is review. I'm just reminding you what you did. But now we have a different thing going on, because now what we want is we're going to let the Hamiltonian become time dependent. And that's the big difference. We're going to have a time dependent Hamiltonian. And so then this doesn't work. Because, and I'm not going to go through the derivation of what you did last semester, because you went through it already. But the reason it doesn't work is because, I'll just remind you, what you did last semester is you used separation of variables. And the separation of variables trick that you did is no longer valid, because separation of variables, the way you did it, at least last semester, it wasn't general enough. Separation of variables technique that you did last semester wasn't general about. The technique you did last semester fails. It wasn't general enough for this situation. It fails when their Hamiltonian is time dependent, because last semester you had the Hamiltonian be a constant. You might not remember this, but I'm reminding you. Okay, and so now we have to do something different. So we have to do something different to take account of this time-dependent Hamiltonian. And so the problem that I want you to, and so the way I want to sort of introduce this topic, I just introduced it right now, but the way I want to introduce it further is let's consider a problem. And so this is in my mind sort of the most important time-dependent problem for you to understand in this course. So consider this scenario, this problem, and it's very general. It's a very general idea. Here's the problem: is like let's consider this scenario, which is that I have a box. You know how much I like boxes. I love boxes. I got a box. I got some eigenstates in my box. So this box could be an atom. It could be any potential that has eigenstates. It could be a simple harmonic oscillator. It could be anything. So, and I got these levels, 1, 2, 3, 4, 5. I got my eigenstates. And let's say that my electron is sitting, my particle is sitting in some level there. And then what I want to do is let's shine light on it. All right. Got a little man. It's got a flashlight. It's got a bulb. Use really a laser. Let's call it a laser, not a flashlight. And he shoots some light at that atom, at that box. And this light is h bar omega, has some frequency. And then the question is, what happens? And you have thought about this. This has been discussed, like in Physics 7c, you talked about this. You've talked about this. I know you've thought about this in some previous class, at least at a very sort of simplistic level. And so what we're going to do in this class is we're going to continue, we're going to sort of extend that discussion. We're going to go into this topic in much greater detail than what you did in the past. But let's try to remember what you did in the past. So these levels have energies, etc. And so I'm going to ask you a question. What happens if h bar omega equals E2 minus E1? Somebody tell me, what happens?
It's going to jump to the second excited state, right?
Perfect. We'll call that a quantum jump, right? That's where quantum comes from. That's why we even use the word quantum. Now, E1 for an atom, if this was a hydrogen atom, can someone tell me what E1 is? What would E1 be if this was a hydrogen atom? Somebody tell me. It's a number.
Negative 13.6.
Exactly, negative 13.6 electron volts, exactly. And so that means that the ground state is going to be, you know, if E is a negative number, then because it's a bound state, so E is a negative number. So what if the light has energy greater than negative E1? Then what happens? And you've also discussed this in some class. I know you have. What happens?
Ionization.
Exactly. You even use the right word. That's good. Ionization. The particle becomes free, jumps out. We'll call that freedom. I'm free. Yeah. Okay. Great. All right. But now I'll ask you a different question. What happens if h bar omega is equal to 1/2 of E2 minus E1? Now what happens? So, and I'll give you a name for this. This has a name. We call this off resonant. Because the condition, this condition here, we call that a resonant condition. So that's a resonant situation. We have resonance, meaning the light is in resonance with the energy transition. But now I've given you an off resonant scenario, and I'm asking you a question. What happens?
It stays in the first level.
And so it never moves? It just sits there?
Yeah, it doesn't have enough energy to jump to the next one.
Yeah, that makes sense. That makes sense, you know, and that's what you learned, you know, in that class. That makes perfect sense. It is totally wrong, but it makes perfect sense. It's logical, and that's a good answer, but it's not true. In fact, that electron can jump all over the place. And how is that possible? And, you know, and how do I reconcile that, you know, with all the stuff that you've learned before? And so the point I want to make is, well, first, let me just write this little answer. We can have transitions. These are called off-resonant transitions. And so how do you reconcile that? Well, that's what we're about to do, okay? I mean, that's why we're going to talk about time-dependent perturbation theory, because time-dependent perturbation theory explains that, you know. And so so what I want to explain is, like, you guys have thought about this a little bit, but there's like a lot more, you know, to this topic. For example, you know, even this simple resonant situation that you know so well, where this I'll call this scenario 1. I could ask you even about that scenario 1. I could say, what is the rate of transition? I could say, what is the probability that the electron will have a transition within, you know, say 35 seconds? And, you know, and so you learned that there's enough energy to make the transition, but you never learned how frequently do the transitions occur. So I could say to you, okay, I'm shining resonant light on this atom or this box or whatever it is, it doesn't matter. But what is the probability that the transition occurs within half a minute, within 5 minutes, within a nanosecond, within a microsecond. All right, so those are the kinds of questions that you actually need to answer in physics. You know, we need to know those answers. Those are important answers if we want. I mean, as physicists, we just want to know them because that's how the world works. But it's more important than that, because if you want to create devices, optical devices, optoelectronic devices, if you want to create a cell phone network so that people could actually talk to someone on the other side of the world just by pushing some buttons, you have to understand this stuff, you know, because all the devices, all the optoelectronic devices in the world are functioning based on these quantum mechanical principles, and it's really important. Okay, so let's learn that. And so this is the question that I want to deal with today, and for really like the next week or two. You know, how do these things occur? Okay, and so let's set up the problem, how to answer these questions. And the main question is, you know, what happens, and how do we understand the time dependence? I'll say this: what is the time dependence? And this is the main question that I want to understand. You know, this is in my mind the most important problem. I got a box, I got a particle in it, like an electron, I shine light on it. What happens? Okay, because if you can understand that problem, then that will really unlock time dependence in quantum mechanics for you, and then you'll really be able to understand many other problems too. I think this is the most important problem. Light hitting a box. Okay, so what happens when light hits a box? So so what we do is we divide time. The simplest way to think about it, and there's many ways to think about it, you know, it's a very deep topic and you spend your whole life studying it, but we don't have that much time. And so let's do it the simple way. And the simple way is to divide time into two parts. One part is t less than 0, and the other part is t greater than 0. Okay, and the reason why I divide time into two parts is that, as I'm going to say, you know, I already sort of gave away, you know, the trick. The trick is that we're going to use perturbation theory to understand this. You know, like, I just want to say, like, you know, we want to understand this scenario that in the little picture, you know, here that the arrow is pointing at. We want to understand that, you know, and the question is, how are we going to answer all these questions? How are we going to understand it? You know, I will just say that, you know, the answer to all our questions is this, you know, h of t psi of t is equal to I h bar d dt psi of t. You know, that's the Schrodinger equation. That's the correct Schrodinger equation where we've left time into it. And so any question I ask you about quantum mechanics, the answer is always this equation. All right, that's the answer. You know that's the answer. That answers that answers every question. But the problem is that we don't know how to solve that equation. It's too hard to solve. And so even though that's the answer to all these questions, you know, what happens when I shine light on a box? What happens if it's on resonance, off resonance, blah, 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 all that. To answer those questions, we're going to do perturbation theory, okay? So perturbation theory. So the Schrodinger equation is too hard. And so what we're going to do is perturbation theory. And you've already been introduced to the sort of concept of perturbation theory, but you've only been introduced to the concept in this time-independent way. Now we're going to bring time into the picture, and things change. It's a little different. But what we're going to do is we're going to divide time into two parts, t less than 0, t greater than 0. And for t less than 0, this is the time which is before the perturbation. And t greater than 0 is going to be the time after the perturbation. After the perturbation. is turned on. And so that's how I want you to think, okay? So when I say to you, what happens when I shine light on this box? This is how you should think. You should think to yourself, okay, well, there's a time t less than 0, which is before I shine the light on the box. And here's my box. And I got my energy levels. Everything's nice and copacetic. You know how to understand it. The particle is sitting in the ground state or some well-defined quantum state. There's no perturbation. No perturbation. And here the perturbation is meant to refer to the time-dependent perturbation. In other words, the Hamiltonian is not time-dependent. That's what I mean now. When I say no perturbation, I mean that the Hamiltonian is just stationary, like a hydrogen atom. So I'm not talking about spin orbit, hyperfine, relativistic correction. I'm not talking about that. When I say perturbation, I'm talking about the light, the external perturbation, external. But then what happens is at t equals 0, then what happens is I shine my light on the thing and everything changes. And this is light, right? Light is an electric field that moves in space. This is E. Okay, that's what light is. It's an electric field. It's a moving electric field. You guys have all seen light before. I mean, in classes, and so you have a sense of what it is. I'll just write it out. Here's light. E of RT is equal to an amplitude, the electric field amplitude times it's a traveling wave. So it's sine of k dot r minus omega t. I'll just add a little phase there, plus phi. Okay, that's light, and you've all seen it before. Although, you really talk about it much more in physics 110A. So I hope that you've taken 110A. That will make things easier, but it's not necessary. It's okay if you haven't taken 110A. I'm not going to get really deep into the electromagnetic aspects of it. Those aspects will just be skin deep. We're going to sort of focus more on the quantum mechanics. And so now what happens is that light hits you. And the question then is, what happens to you if you're in this box? If you're a little particle in this box, what happens to you? Well, here you are. And the point I want to make is that let's look at t less than 0, okay? Let's go back. and I will ask you the question, that electron or particle sitting in that eigenstate, what happens if I never turned on the light? What would happen to that particle? I'm asking you a question. Answer it, please.
You would stay in whatever state it's in.
Exactly, because those are eigenstates, stationary states. Right, that's what you learned last semester. There's no real time dependence. They have that phase, zoom, 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 right? They have a phase that's fluctuating, like, I'll call this one, I want to remind you about that phase because it's going to become important later. Psi 1 of x e to the negative I e1 t over h bar. So there's some spatial part of the wave function, and you guys know that for an eigenstate, the time dependence is very simple. It's just sitting in that phase. Simple time dependence. It's just that phase, but that phase doesn't cause the particle to move, to jump around. It doesn't jump around. Okay, but now we got this new situation. Suddenly we turned on the light. Boom, at t equals 0, we turned on some light. It changes everything. Now it's changed, because what has changed is that these are no longer the eigenstates anymore. Not the eigenstates. Three exclamation marks. Do you see that? Because those were the eigenstates before the light, but now I have turned on the light, so they are no longer the eigenstates anymore. Once the light is turned on, they are not eigenstates anymore. I have a new set of eigenstates. Let's draw them. It's hard to know exactly where they are, because to know where they are, I got to solve the time-dependent Schrodinger equation, which is really hard to solve. So I don't really know exactly where those eigenstates are, but I know they're somewhere, and I know that they're different. And so I get this new set of states. I'm just drawing them sort of as, random. I don't really know where they are, but I have new eigenstates. Those dashed lines are the new eigenstates. New eigenstates. And so now, but the thing is, I'm still sitting in this bottom state here. I'm still sitting in that old state, because here's something that I want you to understand. It's like, if you're sitting in some state in quantum mechanics, things don't change immediately. There's a time. It takes time for things to change, right? And the rate at which things change comes from this time-dependent Schrodinger equation. You can see from this that the rate ddt of my state is equal to the Hamiltonian acting on my state, this equation that you've seen before. So the point is that states don't change instantaneously. You turn on a perturbation, and then they take time, and they evolve in time according to this equation. So the point I want to make is that when I shine the light onto this situation, then my electron is in that original state, number one. It doesn't suddenly, it's not like suddenly gone, and the state doesn't suddenly disappear. The state is still there because the electron is in that state. But something important has changed. And I'll ask you a question. Is that state that the electron is it an eigenstate anymore? Yes or no?
It's not an eigenstate anymore.
That's the important change. That is the big, gigantic change. Is not an eigenstate anymore. It's still in that state, but that state just happens to not be an eigenstate anymore. And so now I will ask you, what now is the time dependence of the electron? It used to be this simple thing on the left. That used to be its time dependence. It used to be a stationary state. Just its phase just goes zip, 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 and the electron won't move anywhere. But now it's no longer an eigenstate. That means that its time dependence is no longer this simple equation on the left. It's something different. So what is it? How do I understand the time dependence of the electron now? And I'm asking you to use, you could answer this question using the reasoning of last semester. It is possible for you to answer this question using the reasoning that you learned last semester. What is the time dependence now? And the answer really, where I wrote it somewhere. Where the hell did I write it? Oh yeah, this is what you learned last semester. It's hard for me to be jumping around, but it's this equation, right? This is the time dependence that this one right there, in the middle of this page. So now let's go to where we are now. And so now I'm asking the question, what is the time dependence of this particle? I've turned on the light. It's no longer in an eigenstate. What does it do? Can anyone guess?
Would you need to find like the new set of eigenenergies and the new basis with perturbation theory? Yeah.
Perfect. That's very good. Yeah, that's exactly right. So we consider the new basis, which are going to be the new eigenstates. Because the thing is, when anyone asks you a question about time, what time is it? When someone asks you about time, you always want to go into the energy eigenstates, because the energy eigenstates, they have the simplest time dependence. And so that's why you always want to be working in the basis of the energy eigenstates. And so you look in the new basis, and so what you want to do is you want to write your wave function in terms of the new basis, and I'll call it here a sub n. I'll do like this. I'll call it phi n of x with a tilde on it times e to the negative I e n. I'll put a tilde on it, t over h bar. So this is the new basis, and so this a sub n is going to be the overlap of your state initially at time equals 0 onto the new basis, where this is the new eigenstates, which include the light. And so this is the same formula as last semester. The same physics, the same thing is happening. It's just that you're not in an eigenstate anymore. And so what you can do is you can just say, well, if I knew the new eigenstates, then I could write down the time dependence very easily, because I just take my old state where I was, which is the one on the left, and I just write the overlap of that state onto all the new eigenstates. And then I write my wave function as a linear superposition of all the new eigenstates. And each of the new eigenstates has a little phase factor, you see? But the problem is that, of course, is that you don't know the new eigenstates. And this is really complicated. And so this is basically a complicated mess. But this is the complicated mess that we want to understand, okay? So we have to understand this complicated mess. That's the point of time-dependent perturbation theory, is to start untangling this. But I want you just to see the problem and to understand it. And without solving any equations, can you guess what happens? What happens to that electron? Can you guess? I know it's impossible to solve all those quick equations. I mean, they're just too hard. But I'm asking you to use some kind of intuition. Think about it. You're not in an eigenstate. You're in some weird state, the original state. That weird state is equal to some weird superposition of the actual eigenstates. And so your wave function is that new weird superposition, and each eigenstate has a phase factor, it's spinning. So it's like this weird, really it's a wave packet, it's this weird wave packet, superposition of all these states. And that's your new state, and they're all spinning, the phases are spinning, and they're all interfering with each other in some hideously complex way. And that's all the language of quantum mechanics, using like equations and complicated mathematical expressions. But those mathematical expressions and all that complicated stuff is meant to describe actual physical processes. So what I'm asking you to do is, sidestep all the complicated equations and just tell me, what do you think is the resulting physical process that all that complicated mathematics is trying to describe? What is I'm asking you for the qualitative physical description. So please tell me that.
Does it just kind of move itself into the new eigenstate? Like it just kind of shifts over time?
Exactly. That's exactly perfectly correct. That is exactly right. Because what happens is all these new eigenstates, the old state is not an eigenstate. So the old state is a linear superposition of the new eigenstates. And so that means that the electron has some component of all of those states living inside of it. And that means that the electron has some probability to be in all of those states. And so that is equivalent to saying that the electron has a probability to jump, to transition to all of these states. Because now the electron is in a linear superposition state of all of those states. So that means that the particle has a probability to be on all of those levels. And that probability will change in time. And that evolving probability is how the particle moves, okay? That evolving probability is describing how the electron moves with time. And so this is what and so the evolving probability is described by this wave function. You have an evolving probability And if I said to you, what is the probability? Well, let's not get into it. That's okay. I'm just going to stop there. So I want you to sort of get some sense, that this is what's happening. This is what we have to understand. We want to understand this evolving probability as you start moving through these different eigenstates. Okay, so this is sort of what's happening. But now let's
Professor?
Yeah.
I just feel it's weird for me, it's really like weird that the position states are also affected by the time independency of Hamiltonian, but like from my first intuition, I thought just the time dependent part would be that exponential term would be affected, but I'm kind of having a hard time why that position state is also affected by the time dependent perturbation.
Well, it's like this. I mean, this is the way to picture it. Let's look at an atom, a hydrogen atom, okay? Classically, that's what it is. And so now, what's going to happen is I'm going to shine light on that hydrogen atom, and the light is this. Okay, so E is equal to E naught sine KR minus omega t plus some random phase or whatever. So this is my light that's going to hit that atom. And let's sort of deconstruct a little bit. I'm trying to answer your question, but I feel like this is like a nice way to answer it. So before we do anything, I want to ask you a question. What's the wavelength? Or I'm not asking you specifically, but anyone who can tell me. What's the wavelength of light? What's the wavelength of optical light? How big is it? How big is light? Somebody tell me.
A few hundred nanometers. Like 5 or something.
Yeah, let's see. 100 nanometers is 1,000 angstroms. Yeah, that's right. Yeah, a few hundred nanometers, like let's say 500. Say, yeah, that's right. So that means it's like let's call that half a micron. It's like half a micron. Let's just call it 500. Just pick a nice round number, 500 nanometers. And that's like the 500 nanometers, I think is, does anybody know what color light that is? I think it's green light. Does anybody know 500 nanometers?
I think it's green, yellow. Somewhere.
Yeah, okay. It's nice optical light. It's green, something we can see with our eyes. Okay, so that's a nice green light. That's half a micron. But let's not use microns. Let's use angstroms. 5,000 angstroms. I'm using angstroms because when we talk about atoms, an angstrom is the natural length scale, because the diameter of a hydrogen atom is how many angstroms?
1.
Yes, exactly. Atoms are pretty damn tiny. So what happens is this light wavelength is 5,000 angstroms, and the atom is just 1 angstrom. So first I want to ask you, does the atom actually, can the atom tell that it's being hit by a wave?
Probably not.
That's right, because the wave is too big. So from the atom's perspective, what is happening? What does it see? So, here's the little man. Now instead of a flashlight, just give him a laser. And he shoots his laser at the atom. And it's let's call it a green laser, okay? And what does the atom experience?
Nothing.
No, it does. It experiences something. Yeah, it gets hit by a laser, man. If you get hit by a laser, you get a green dot, right? But I mean, the atom knows it's being hit by a laser, but what does it experience? What does it see? What does it feel? How does it feel? How does it smell? What does it smell like? No. Somebody tell me though, what is that atom experiencing? It gets hit by the laser. What does it experience?
Is it like comparable to like being a tiny boat on like a big ocean wave, and it just kind of starts to move from the wave, but doesn't really realize that it's like a wave hitting it, but like it kind of just feels it move?
Yes, that it is. Okay, let's use that analogy. So I'm in a little boat and this giant wave comes along, but this wave is so long that I can't even see the end of it. It's just so big. So this big wave, I'm in the boat, this big wave comes, it hits me, I'm in the boat, I get hit by this big wave. It's not crashing, okay? It's not like a crashing wave, but it's a wave that just comes on the sea. I'm in my boat. What do I experience in my boat? Tell me more specifically. I mean, that's a good analogy, but I want it to be more specific. What do I specifically experience in my little boat?
Rising and falling?
Yes. I go up, I go down. I do not know that there's a wave. All I experience is that the ocean goes up and down, periodically in time. Okay, that's what happens. And so the point I want to make is that this atom experiences this. The thing is that the location is fixed in this equation. And so basically what the atom sees is E. It sees a time dependence, not a spatial dependence. This is what the atom experiences. This. It feels this electric field that's up, and then it's down, and then it's up. So the atom is experiencing this electric field like it's pointing up, and then it's pointing down, and then it's pointing up, and then it's pointing down, okay? And what does the electron feel? What is the force on the electron? Because we're talking about the electron, the proton is so big and heavy and stationary, we don't care about it. The electron is the little guy who moves around. So let's worry about the electron. Let's assume that the nucleus is just stationary. So what is the force? So what does the electron actually feel? What is the force on the electron? This is not a hard question. This is like
charge times electric field.
That's exactly right. That's exactly right. And so the charge, and so the force is going to be minus E naught sine omega t. So this is purely classical. Okay, we're not talking quantum mechanics yet, but the classical gives you insight into the quantum mechanics, because eventually when we do quantum mechanics, we're going to have to construct a Hamiltonian, and that comes from classical mechanics. So a classical mechanics discussion is very important in quantum mechanics. So, okay, so that's the force. So the electron in that atom feels this force. That's what it feels right there. I wrote the equation for it. And that's a significant thing. That means that the electron is being pushed up, and then it's being pushed down, and then it's being pushed up, and then it's being pushed down. And so something is definitely happening to that electron. It's being pushed up, down, up, down, up, down. And so that is the answer to your question. I forget who even asked me the question. Sarah, maybe? I can't remember. But this is the answer to your question. It's like, definitely something is going to happen to those energy levels, because the electron is, before the electron was just only feeling the tug of the Coulomb potential. And all the energy levels were determined by the tug of the Coulomb potential, that stationary tug. And you solved it last semester, all you got the psi NLM. But now I'm adding a new thing. Now I'm adding a force. That electron, which used to only feel the tug of the Coulomb potential, is now being pushed up, down, up, down, up, down. And so that's something, and so that's the answer to your question. That's what's causing those energy levels to shift and change. So something is really happening. Okay, that's like the best I can do.
Yeah, that makes sense. Thank you.
Okay. All right. So now the question is, what does happen? Like I just sort of set up the scenario, and so how do we understand what happens? So what we have to do. So the question, of course, is then, you know, I'm shining the light on the atom, and then the question I will always ask is, what happens? And the picture is this. And I will remind you, because it's the same picture over and over. I'm sitting in some well-defined state. I shine light on it. And then the question is, what happens, right? And so to answer that question, we have to solve this, the Schrodinger equation. I h bar d dt psi of t. That's what happens, okay? This is the answer. Okay, but this is a tough answer. But before, you know, and it's going to be too hard to solve exactly, but we're going to use perturbation theory to solve it. But before we can even apply perturbation theory to this equation, which is the Schrodinger equation, what are we missing? What's the important thing that we need? Tell me. What do we need?
Do we need the Hamiltonian first?
Exactly. What is the Hamiltonian? All right. And so the thing that the part of the Hamiltonian that we're missing is the part that comes from light. So to get this Hamiltonian, we need to think classically. And we already talked about it. We said that, well, if I have light shining on an atom, I mean, I already have it up here. You know, I wrote the equations up there. I'll rewrite them down here. Classically, we know that there's a force, Q times E, which in our case is minus E times E. And we know that the electron, we know that the wave gives us an electric field that goes up and down, right? Sine omega t. So that's the force that the electron feels. Okay, good. But now I have the force. How do I get the Hamiltonian? You got the classical force. Somebody tell me how to get the Hamiltonian. How do I get a Hamiltonian from this? Tell me.
Well, you need like the potential and the kinetic energy. So.
But I'm only wanting the part that you're right. You know, the total Hamiltonian will include the kinetic energy. You're totally right. But I'm only asking for the part that comes from light.
Could we find the kinetic energy with the work energy theorem by finding the work from this force equation?
Okay, yeah. Although I'm not. I don't want to talk about kinetic energy right now because you remember we're doing perturbation theory, you know, and so the perturbation is the light. So you're correct. You know, the kinetic energy is in the Hamiltonian, but that's going to be in the H naught part. You know, the unperturbed part. I just want to know the perturbation, the light. So what is the Hamiltonian that comes from the light? Because this is the force that comes from the light right here. So now I'm asking, how do I turn that force into a Hamiltonian?
Then the potential that arises from that force.
That's exactly right. And how do I get that? What's the relationship between force and potential? F and
Do we integrate it?
that's exactly right. But that's exactly right. But can someone just tell me what is like an equation that there's a very famous equation that links these two things. Like I can say force is equal to what?
The negative gradient of U.
Yeah, exactly. There you go. That's right. That's what I was looking for. That's what I wanted you to say. And I know you all know this formula, but you just didn't know that's the one I was asking for. You've all seen this a million times. Okay, that's the formula. And so what that means then is that U is equal to negative integral from 0 to R f of R prime dr prime, right? So there we have it. Or am I doing it right? No, I'm not doing it right. Let's get it right. F of r dot dr. There we go. Prime. Yeah, did I get it right? That's it, right? Yeah, did that look good? And so let's do this integral. So then this is going to be, but let's just do it in one dimension, okay? We don't need to do it in all the dimensions for now. So, and the reason is because the reason I only need to do one dimension is because the electric field is only pointing in one direction. So that's why it really reduces to a one-dimensional problem. That's quite nice, at least initially. And so this will be negative integral 0 to r, or let's do x, I'm sorry, one-dimensional problem. 0 to x, f of r is going to be negative e naught sine omega t, right? That's my force. Dot x dx. And so it's going to be these negative signs cancel. And it's basically just going to be u of x is equal to e naught dot x hat sine omega t. And so let's pick the electric field. Let's pick the x-axis to be in the direction of the electric field. So then, did I get, yeah. Then let's pick x hat parallel to e naught. And so then I have u of x is equal to e naught. Oh, and then there's an x. I'm sorry, I missed the x. Shit, it's the most important part. E naught x sine omega t. Okay, how does that look? Is that right? Did I get that right? Does that make sense, folks?
Yeah.
Okay. So yeah, so it's pretty simple actually. Yeah, and I think you've seen this before somewhere, but in a capacitor model or something, you've seen it before. Okay, now I do want to mention that there are more, I'm not going to get into the details, but I just want to mention to you there are more sophisticated ways of dealing with this. I mean, I do want to just point out that an electromagnetic wave is the time-dependent electric field, but there's also a time-dependent B field too. And I don't want to get all into this, but I just want to mention it to you, you know, that there is a B field that's changing in time as well. You know, like, so an electromagnetic wave has an electric field and a B field that are perpendicular, and they're going doink, 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 doink as they move. So it's kind of complicated. And so what we're doing is we're ignoring the B field. And it turns out that that's okay, because the B field part, the part comes from the B field for atomic physics. It's usually not very strong, so we can ignore it. It's okay, but it's an approximation. You know, what we're doing is not completely correct. So this very simple treatment that we did just now is good enough for us. But I just want to mention to you that there are more sophisticated treatments for how to deal with the electromagnetic wave as it hits some system. And sometimes you do need to do a more sophisticated treatment, okay? Sometimes you actually do need to do the more sophisticated treatment for certain systems, but most of the time you don't have to. So I'm not going to get into all those details. You can learn that in graduate school. But I just want to mention to you that it exists, because I don't want you to go out, you know, and then someone's going to say, this is how you do, you know, light hitting an atom, and then suddenly they're using the vector potential, and you're like, what the hell, why are they doing the vector potential? And I just want you to see that I just want to mention to you that, you know, there's other ways to do it, more sophisticated ways, but what we're doing now is good enough for us and for like 99% of things. Okay, so that's the potential, and so that means that that's the Hamiltonian. So we have just figured out the Hamiltonian. The Hamiltonian is now time dependent, and it's the charge of the electron, E naught times x times sine omega t. We got it. Okay, and so that that is what the particle feels as I shine light on it. The particle is living in this box, and it gets the light shined on it, and that's what it feels. Okay, so there's a time dependent Hamiltonian, and so this is the first time that you've seen a time dependent Hamiltonian, supposedly. So now the question is, okay, so we got our time dependent Hamiltonian. So now what we have to do is solve the Schrodinger equation to figure out, because the question is always the same. What happens? Okay, you know, I have t equals 0, which is before the perturbation, and then I have t greater than 0, which is after the perturbation. And the question is, what happens for t greater than 0? That's the question. All right, and so to answer that question, we've got to solve the Schrodinger equation. So let's solve it. We have a time-dependent Hamiltonian, and so let's solve the Schrodinger equation. It's pretty hard to solve, but we're gonna make a bunch of approximations. So let's do this. So what we're gonna do is, you know, like, remember what I said is that we have our eigenstates 1, 2, 3, 4, and these are the eigenstates before the perturbation. Okay, I'll call these the old eigenstates. Actually, I'm going to use the language of perturbation theory. In the language of perturbation theory, we call these the unperturbed eigenstates, and you guys are used to that language. I've used it before. So these are the unperturbed eigenstates, and you know what they are. You know them. They are. There's an H naught, and I'm going to use this notation. I'm going to call them phi n of x. And you know that H naught phi n of x is equal to E n phi n of x, where this is the unperturbed states. Unperturbed states, and these are the unperturbed energies. And this is what you know, okay? But then what happens is at t greater than 0, what happens is that H, the Hamiltonian, turns into H naught plus H of t. Maybe I'll put a little prime here because it's a perturbation, where this perturbation is light, E naught x sine omega t. Okay, so this is the situation. And initially we're sitting in some state. I'll just say the state number 1, doesn't matter. We're sitting in one of those states. And so we turn on the perturbation. So then the question is, let's assume that initially we're in, actually I'm gonna make this more general, and I'm gonna say that initially we're in some arbitrary kth state. So what that means then is that my wave function at time t equals 0 is equal to phi k of x. Okay, so I'm initially in the kth state, initial condition. And then I turn on my perturbation, and what happens? Well, I already described it qualitatively. We get mixed up. We're getting mixed into all these other states because we're no longer in a good eigenstate. How do I describe that? So mathematically, I can write it like this. I can say that at some later time, t greater than 0, my wave function is going to look like this. I'm going to write it as a linear superposition of the, I have to pick a basis. I'm going to write my wave function in some basis. Now, I have to pick a basis. What I would like to pick is the eigenstates of the new Hamiltonian, the correct eigenstates as my basis, but I don't know what they are, so I cannot use those. So the only basis I know is the old basis, the unperturbed basis. Unfortunately, I got something in my eye. So I have I only know the old basis. So I'm going to write my wave function as a linear superposition of the old basis. And so I'm going to write it like this. And then there's a time dependence where every one of these basis states has I'm going to give it a phase factor. Now, this is not the right way to do it, because we know that these are not the new eigenstates. And so we know that the time dependence is really complicated now. It doesn't have this very simple rotating phase factor. So this is what you would have done last semester, but you can't really do it this semester because it's, this is not, these are not the right eigenstates. So I have to compensate for that. And the way I'm going to compensate for that is I'm going to do this. I'm going to say, well, there's a factor here, Cn. Now in the old days, last semester, that would just be a constant, but now it's a function of time. And so this is the key point. That is the key point. So this is a really important equation for you to understand, because I'm saying that my wave function is a linear superposition of all the eigenstates of the system, the unperturbed eigenstates of the system, times this unknown function of time, Cn of t. But what is this Cn of t? What's going to happen is the Cn of t, the way you interpret that, what that is the overlap of the wave function at time t on the unperturbed eigenstate phi sub m. All right, so I'm going to ask you a question. Suppose I do a measurement. Suppose we measure the electron energy at some later time t. Then my question to you is, what is the probability to measure E3, where that is the unperturbed n equals 3 energy? This is I picked, well, let's not pick n equals 3. Let me pick a different one. I'm going to pick 4. And this is what I'm talking about. Like, this is n equals 4 right here. N equals 4. What is the probability that I find the particle is in the n equals 4 state? That's what I'm asking you.
The C4 squared.
That's exactly right. And is that a function of time, C4?
Yes.
That's right. That's exactly right. That was a great answer. That's exactly right. I have something in my eye. I gotta go see if I can get it out. Hold on. All right. So that's, yeah, so that's the key point, which is that, now my hands are wet. So that's the key point, is that that's the probability. So in general, if I measure the energy, then the probability that I'm going to get a measurement, the probability that I'm going to measure, that I'm going to be, the probability that I'm going to be in the end state at time t is this: probability to be in nth state at time equals t is this, and that is going to be Cn of t squared. And so that is the key setup. So this is, so I want you to really absorb this, because this is like the important setup for time-dependent perturbation theory. If this doesn't make sense to you, then time-dependent perturbation theory will never make sense to you. Okay, so I realize that for many of you this probably doesn't make sense, but the reason I'm saying this is because this is what you need to understand. Okay, I just want to point out to you, please, try your hardest to try to have this make sense. Because what I'm doing is I'm writing the unknown wave function, which we haven't solved yet, but the point is I'm writing it as a superposition of the unperturbed states, which I can do because that's a complete basis. Even though they're no longer the eigenstates, they're still a complete basis. So I can always write my wave function in terms of them. But now I have all this crazy time dependence, and the time dependence I'm putting into this function Cn of t. So this function is the most important thing. And if we can find out what that Cn of t is, then it tells us the amplitude to find the wave function in that particular unperturbed eigenstate. And to get a probability out of it, we just square it. And so the language that we now use is we say that this is the probability to have and this is the language we use, we say a transition to nth state. So now we're using the language of transitions. So this is the probability that we have a transition to the nth state. So this is the way you should see it then. It's like this. I'm sitting in some arbitrary state. Let's just say I'm sitting in this state, which is the kth state, and then I get hit by some perturbation, the light or any perturbation. And then what happens is I have a probability to now transition to every other state. There's some probability that I might go to any state. I might go to all of them, in quantum mechanics, I have a probability to go to all of them. And so what is that probability? So the probability to go to the nth state is going to be Cn of t squared. So that tells me the probability of transition, probability of transition. So that's the language, that's how we're going to think about it. So now clearly the thing that we must find is that function, must find Cn of t. And let's go back to this equation here. Here is the Cn of t. I've written it right here. When I talk about time-dependent perturbation theory, there's a language I like to use. There's words I like to use that, sometimes we talk about probability, sometimes we talk about amplitude. So this quantity, what is Cn of t? What the hell is it? Because Cn of t squared is probability. But what is Cn of t itself? What do I call it? What is it? If I'm using a word to describe it, what is the word that I use? What quantum mechanics word is it? Can someone tell me?
Coefficient? I'm not sure if it's a quantum mechanics word, but
It's what?
Coefficient, I said.
It is a coefficient, but it is representing a physical quantity. What is the physical quantity that it represents? And that's kind of a confusing question, but quantum mechanics is confusing. You know, it's like, because you know that it's basically the square root of probability, right? Because if I square it, it's probability, so it must be the square root of probability. But that's not exactly right, because probability is real, whereas Cn of t, well, I'll ask you, can Cn of t be complex? Yes or no? Yes or no?
Yes.
Correct. So that means it's not exactly the square root of probability, since probability is a real number. What is Cn of t? What does it represent physically? It's a physical quantity. What do we call it in quantum mechanics?
The probability density.
No, that's wave function squared. Although, you know, that was a good guess. You know, psi star psi is probability density. This is psi. It's not psi star psi, it's just psi. So really what I'm asking you, you know, Cn of t is the same as the wave function, right? It's, okay, this is the word I'm looking for, amplitude. And I know it was a trick question, but I sometimes like to do trick questions because it makes you think. And hopefully it'll help you to remember that. So, because I like to use that word amplitude. Cn of t is an amplitude. An amplitude, like a wave function, is amplitude. And to turn amplitude, to get probability, you got to square the amplitude. And the reason why I got to give it a name is because the interference, quantum interference, happens with amplitude. When I start adding up amplitudes, they add and subtract from each other, and that is what we call quantum interference. So, you know, amplitude is where all the quantum interference happens. So Cn of t is the amplitude. We got to find that amplitude. So how do we find it? How? Well, let's think about it. I have this. I have the Schrodinger equation, and this is the Schrodinger equation. H of t acting on psi on my wave function is equal to IH bar d dt psi of xt. And I also know that psi of xt is equal to this, Cn of t, the amplitude to be in the nth state, times the unperturbed state, times this little convenient phase factor. And this is completely general because Cn of t is still not defined. So this is still, so this is, we haven't done any approximations yet, no approximations yet. But of course, as you know, we're going to make a ton of approximations soon. Okay, I got my wave function, I got my Schrodinger equation, and the thing is, this is what we want. How do I get it? What do I do next? Now tell me what to do.
We plug in the wave function and then apply the Hamiltonian to each of the eigenstates.
Yes, that's exactly what we do. And we also know that the Hamiltonian is H equals the unperturbed Hamiltonian plus the perturbation, okay? Where in the language that I've been using, this would be, for example, the box, and this would be the light. So so what we do now is we just plug it in. That's exactly right. Plug it in and do some tedious algebra. And it's not hard. Let's do it. So so let's do it. So H is H naught plus H prime of t is acting on my wave function. And and my wave function is this. It's going to be my amplitude Cn of t times the unperturbed eigenstates times the convenient phase factor, because that's the phase factor they would have. That's the phase factor that an unperturbed state would have. That's why we keep it. Is equal to IH bar, but now I'm going to turn IH bar into a negative H bar over I. I'm just going to put the I underneath and get a negative sign because that's convenient to me to do that. Times d dt times psi, which is, of course, the same thing. Okay, there it is. And now let's just grind through the algebra. And it's really quite amusing to do so. So because what we notice is that when this thing hits this thing, what does it turn into? Somebody tell me.
En.
Yeah, we know it. That's nice. So what we're going to get then, so when we do this algebra, we're going to get this. N, and it's going to be E, N, C, N of T, because of what we just said, phi N. And now I'm going to write, to do the algebra, I'm going to write phi N of X. I'm just going to write it as phi N because it's easier to write. So it's just notation, okay, because easier to write. E to the negative I, E N T over H bar, plus sum over N, H prime of T, Cn, phi N, E to the negative I, E N T over H bar. And this equals the thing on top. And the thing on top, I'm going to take the derivative, but I'm going to have to use the chain rule. Chain rule when we take the derivative. So let's do that. So let's do the chain rule. It's not so hard. That's going to be negative H bar over I. And let's do the first one. Sum over N. And now when I do, when that derivative hits the exponent, it's going to bring out negative I over H bar En. Do you see that? You see how I brought that out of the exponent? Times Cn phi n e to the negative I En t over H bar plus negative H bar over I, the sum over N. Now I got to take the derivative with respect to t of the function Cn of t, which is a time-dependent function, times phi n e to the negative I En t over H bar. Okay, so just chain rule, so it's just algebra, nothing fancy here. So this is, you know, all of you can do this, but there's something cute to notice. I want you to notice how this factor hits this factor, and it turns it into a 1. You see that? Did I get that right? This is a negative 1. Did I get the sign right? I hate getting these little. Yeah, I got that right, of course. Okay, and so you see that it turns it into a 1. And so now I want you to notice that what can we say about this term and this term? And they're on opposite sides of the equal sign. What can we say about those two terms? Somebody tell me.
They cancel out.
Yes, exactly. Cancel. That's exactly right. They cancel. And so that means then that what we have left is going to be this. Negative H bar over I on the left, and T Cn of T. I'm just rewriting it the order, e to the negative I En of T over H bar phi n is equal to N C Cn of T times e to the negative I En T over H bar times H prime of T times phi n. Okay, so, you know, it's not a very intuitive expression, but, you know, it's what we got. And so let's keep going because it will become more intuitive later. What we're going to do now, we're going to do a trick. And the trick that we're going to do is we're going to multiply, we're going to left multiply by an arbitrary state. And we've done this before. We're going to left multiply by the complex conjugate of an arbitrary state. And then we're going to integrate both sides over x. Integrate over x. Okay? That's what we're going to do. And it's not hard. We're just going to do, let's just do it. And so what we're going to do then on the left-hand side is negative h bar over I, because we're doing the same thing to both sides of the equation. So the equation is still good. Got to remember, you got to do the same thing to both sides, right? And then it's okay. You can do whatever you want as long as you do it to both sides. D dt of c sub n e to negative I en of t over h bar. And this is going to be an integral from negative infinity to infinity of phi sub m star of x phi sub n of x dx is equal to the sum over n c n e to negative I e n. I realize I'm just going to go over like just a couple minutes, but you know, if you have to leave, just leave and you can look at the recording for this last little part. Negative infinity to infinity phi m star of x h prime of t phi n of x dx. Okay, so this is what I got. And so now I'm going to give these guys some names. So this part, I get he's equal to what? Tell me. Well, are these two functions orthogonal to each other? Yes or no?
Kronecker delta of mn.
Exactly. So that means then that this n goes to m here. See? Because of that Kronecker delta. And this thing, we're going to give it a name. We're going to call this h prime m n, because this is and it's a time-dependent function, but this is a matrix element, right? So this is the matrix element of h prime that connects the two states, m and n. It's a matrix element. So we're back to that matrix element lingo. And so using this lingo, then what we end up with is this. Now I'm just going to skip, I'm just going to do a little dividing. I'm going to skip a little bit of algebra, skip some algebra, and we get the answer. And the algebra is easy. Skip some easy algebra, and then we get this answer. We get that the time derivative of the m is in Mike, m of t is equal to negative I over h bar n h prime m n of t e to the negative I e n minus e m t over h bar c n of t. That's what we get. And so this is really the central equation of time-dependent perturbation theory. So this is, and it's still exact. This is an exact equation. We haven't made any approximations. And I would call this the central equation of time-dependent perturbation theory. Because this is the equation that we have to solve. Solve it to get Cm of t. Because if we can solve that equation, then we're going to get those C's, those functions, which is the thing we want the most. That's the whole point. Okay, folks, that's where I'm going to stop. So bye-bye. Bye-bye.